In this section, we're going to be talking about what the matrix inverse is and then how that relates to determinants. So for kind of some motivation, think of this in terms of just an algebraic equation. So for any algebra equation of the form ax equals b, if I asked you, solve this equation, well, you would think to yourself, well, usually that just means solve for x, right? So if I were to solve for x, how would I do that? Well, I would say, okay, I'm going to divide both sides by a. And so then they cancel out, and I'm left with x equals b over a, right? And so we have solved the equation. So then that question makes me think, well, could I do that for matrices? Like if I had a matrix equation that looked like ax equals b, would that be possible? And the answer is kind of, but there's a problem with matrices in that they actually don't have division as an operation. So we kind of have to figure out a way of getting around that. So then we think, okay, I divided both sides by a, but what if a was a fraction? If you remember how we solve for fractions, we would multiply both sides by the opposite of the fraction or the reciprocal. So we could also solve this by using the following technique. So we still have ax equals b, but instead of dividing both sides by a, what if I multiplied both sides by 1 over a and 1 over a? Well, on the left side, they cancel out. So I get x equals, and then b times 1 over a is b over a. So we effectively found the same solution, just kind of looked at it in a different way. And it turns out that that 1 over a is actually something very special in mathematics. So we call that the multiplicative inverse. Now you don't have to remember that, but we used the multiplicative inverse of a to cancel it out, and effectively say that anything times its multiplicative inverse will essentially be equal to 1. So that's actually the true definition of multiplicative inverse. Anything times its inverse is equal to 1. And so we have a notation for that. So instead of using 1 over a, because we're kind of lazy, we say a times a to the negative 1 is equal to 1. Now, if you remember exponent rules, 1 plus negative 1 would be 0, and then a to the 0 would be 1. That's not how it works. It just kind of conveniently looks like that. So we have basically introduced this new notation of inverse, right? So multiplicative inverse. There's this special element or number that when you multiply it by another number, it basically goes back to being 1. And that's very special in mathematics, actually. So we're going to use that motivation to solve the matrix equation, right? And so how do we do that? So now, suppose you have the matrix equation. So A is a matrix, X is a matrix, and B is a matrix, right? There's no division in matrices. You can't divide A over because that's not allowed, okay? But if you think back to the multiplication properties, and if you think back to when we learned what the identity matrix was, which is like the 1 matrix, right? And then we even have a 0 matrix too. It turns out that you can modify this equation or manipulate it in a special way that allows you to solve it, assuming there is an inverse, right? So, suppose that A inverse exists. We don't know what it is yet, but let's just pretend it's there, right? Okay. If it exists, then I take my equation, AX. And if you think back to what we learned in matrix multiplication, order matters. So if I want to cancel out A, because remember, A times A inverse is equal to 1, it got rid of it, I should do the same thing. So I'm going to multiply both sides on the left side, though, because order matters. So if I do it on the left side on one side, I got to do it on the left side for the other. And this right here will cancel each other out. And the matrix that we use for 1 is going to be the identity. So it's called the identity matrix. And that's just kind of like the 1 matrix, essentially. So this becomes I times X equals A inverse times B. And then anything times 1. So if you think like, what's 5 times 1? It's 5. 2 times 1, 2. So the identity times X is just X, right? And so X equals A inverse times B. And so we've effectively solved the system using an inverse, right? Well, then the obvious question becomes, well, how do I find that inverse, right? Oh, here's something kind of cool about this, and we'll talk about it later. This is going to be a unique solution every single time, okay? So that's nice. It's always unique. So we have some conditions that we need to satisfy to be able to take an inverse, right? So in order for an inverse to exist, it must be square. So you can't do this for non-square matrices. So it must be square. And if you row reduce it, it becomes I. Okay. So if you think back to row reduction in the previous video, whenever we did the row reduction for a unique solution, it always became that 1, 0, 0, 1 or 1, 0, 0, 0, 1, 0, 0, 0, 1. That's not by chance. That's exactly what's supposed to happen. And so if the inverse exists, that always has to happen to that matrix. So that's kind of, again, a nice property of it. So then what is the definition for an invertible matrix? Well, let A and B be n by n matrices. So n by n just means it's square. A is invertible if the product, so A is invertible if you multiply it by B, this random matrix B, and the order doesn't matter. You get the same thing. And they both equal the identity matrix. So if A times B equals B times A, it's going to be equal to the identity matrix. And so we can say B is an inverse of A, and B is equal to A inverse. So now we can rewrite the notation. And it doesn't matter what order you do it in, which is nice. You get the identity matrix. And if you look back to what we did earlier, that is what happened, right? And again, the motivation for that was for any random number, if you multiply it by its own inverse, you get 1. You would think that would happen for matrices, and the good news is it does. So, hooray. Now, this is a little complicated the first time you hear it. So the good news is you don't have to like truly master this or understand like the theorem or the definition of this to really be able to find the inverse, because the inverse is just a technique, right? And specifically in Mat 211, you're not really going to find inverses of anything bigger than a 2 by 2 matrix. So you just have to understand what an inverse is. It's a matrix that when you multiply it by another matrix, you get the identity matrix, and then you just have to be able to take 2 by 2 inverses, which is just a nice formula. 3 by 3 inverses and bigger, you would have to use row reduction, which, is everyone's favorite. So example, R A equal to 1, 2, 4, 7, and B equal to 3, 1, negative 2, 0, inverses of each other. Well, you just do A times B and then B times A. So A times B is equal to, and you know what? Let's just practice doing matrix multiplication, but of course, why not use your calculator if you can? So 1 times 3 is 3, plus 2 times 2 is -4, so it's a -1, right? This times this gives us -1, and then row 1 and column 2, so 1 times 1 is 1 plus 0, and then 4 times 3 is 12, minus 14, -2, and then 4 times 1 is 4, plus 0 is 4. And then I do B times A. And so if I do not get the same matrix, they are not inverses of each other. So we swap the order. 1, 2, 4, 7. And so 3 times 1 is 3, plus 4 is 7. So immediately, I already know they're not inverses because those two numbers don't match. 6 plus 7 is 13. -2 times 1 is -2 plus 0. -2 times, whoops, I think I went the wrong way. -2, yeah, 4. Nope, -4. Now we're good. So AB does not equal BA, not inverses, right? And there you go. That's not saying A and B don't have an inverses. I'm just saying these two are not inverses of each other, because you would not want to use this technique to actually try to find the inverse, because you would be guessing and checking forever since there are infinitely many matrices. Okay, so one thing that you want to be able to do is, solve for a matrix variable. So here's a quick example, just kind of using rules. So let A and B be invertible, solve for X, right? So if I give you a random equation, something like this, and I said solve for X, so you want to get X by itself, right? So you're just using properties of matrices to kind of do this. So you're going to distribute. And so when you distribute, if it's on the left side, it has to be on the left side. So A times X plus A times B equals B. And then I want to get X by itself. So I'm going to subtract this over. You're allowed to subtract matrices to the other side. So B minus AB. And then I can't divide A over, but I can multiply both sides by the inverse of A, like that. And I never give myself enough space with these. And so we do this again. Whoops. So A inverse. They effectively cancel each other out. I mean, you could write the identity matrix, but you don't even have to do that. And then you get A inverse times B minus AB. Could you distribute that A inverse? You could. You don't have to, because your goal was to get X by itself. But if you wanted to, it would be A inverse times B. So I'm distributing minus A inverse times A times B. And then these right here cancel each other out. And so X is equal to A inverse times B minus B. And if you wanted to keep going and simplify further, you are more than welcome to. But this is a good, simplified answer. If you wanted to go, I would have stopped here though. This is perfectly fine. So that's how you solve for it. And just a reminder, because we did this one earlier, solve the system AX equals B, right? So what could happen, and I'll just use capital letters because sometimes I prefer lowercase for those, but in case they use uppercase, let's just practice. So solve AX equals B, given that A inverse is equal to 1, 2, 3, 4, and B is equal to 1, 0, okay? So AX equals B, if I'm solving the system, that means find x. So I multiply both sides by the inverse. Remember, left side. These cancel each other out, and you're left with x equals a inverse times b. And because I know what the inverse is, they gave it to me. If you're wondering, where'd the inverse come? In this problem, they just gave it to you. 1, 2, 3, 4. B is given to me, 1, 0. It's just a matrix multiplication problem. So 1 times 1 plus 0. And then 3 times 1 plus 0 is 3. And there you go. I solved my matrix system using the inverse. And what you're going to have to do is, well, I'm not going to give you the inverse. I'm not going to be that nice. So you're going to have to find the inverse first before you can actually do this technique, right? So that's what we're going to do next. So to do that, we are going to do the 2x2 inverse. So the 2x2 inverse is just a formula you got to memorize, okay? So given a matrix A equal to A, B, C, D. If you prefer the A11, A12, and A21, A22 notation, it's the same thing. And I'll do both. The inverse is equal to, so you're going to have this fraction in front of it, 1 over AD minus BC. And then you're going to take the main diagonal, which is A and D. You're going to flip them. And then on the off diagonal, you're going to multiply them by -1. Okay, so whatever number's there, change the sign. It'll either be, if it was a negative, it becomes positive. If it was positive, it becomes negative, right? And that's it. If you want to use the other notation, just so that we can kind of keep getting used to it. A11 for row 1, column 1, 1, 2, row 1, column 2, 2, 1, 2, 2. Then the inverse is equal to 1 over A11, A22 minus A21, A12. Again, I prefer the ABCD version of it, but whichever you prefer, by all means, stick with that. Don't swap the order of the off diagonal. They just become the opposite sign. And another mistake I see a lot of students make is they just put plus for the bottom of the fraction. It's always a minus sign. Now, if one of the numbers, B and C are negative, they can make it a positive sign, but by default, it's a negative sign. So always make sure you pay attention to that. So finding the inverse of a 2x2 is as simple as just calculating the formula, right? So find a inverse of A equal to 1, 1, 1, 2. Well, step 1, formula. The inverse is equal to 1 over AD minus BC, DA, negative B, negative C. Step 2, plug in. So the inverse is equal to 1 over 1 times 2 minus 1 times 1. And then the 2 and the 1 swap spots, -1, -1. And then I get 1 over 2 minus 1. So that becomes a 1. And then 2, -1, -1, 1. And so my inverse is 2, -1, -1, 1. Now, most of the time, fractions do come out when you're taking the inverse. So very rarely is it actually nice numbers, unless they design it that way. But that's how you find the inverse of a 2x2 matrix. Now, usually they're not going to, make it too easy for you. But if you do want to use your calculator, I mean, your calculator can also calculate it. So second matrix, go to edit. And then we can just type in the numbers. I would always maybe reset it, but this is a very simple matrix. So second quit, pick your matrix A, and then hit the little inverse button. So x to the -1, and there it is. All right, so you could easily do it that way too. But in practice, they're going to make it more challenging by throwing in a letter in there, because then your calculator can't really do it, right? So here's an example that they could do. Now, notice, before I continue on, note that 1 over AD minus BC can divide by 0 if AD minus BC is equal to 0. Okay, so we don't ever want that. So we can say a matrix is not invertible, and a word that you will see when it's talking about non-invertibility is potentially singular. So a singular matrix means not invertible if AD minus BC equals 0. So if you run into a matrix like that, that means not invertible. So here's an example they can ask you. For what value of K is A not invertible? Okay. And so they give you a random matrix. Now, you don't actually have to find the entire inverse. I just want to know what K makes it not work. What's the bad K value, right? So set AD minus BC equal to 0 and solve for K. So 7 times 6 minus 2 times K, right? A, B, C, D equal to 0. 42 minus 2K equal to 0. Negative 2K equals 42. K is equal to negative 21. So that number will make the matrix not invertible. So no good, right? We're going to learn in a second that that number actually means the determinant. So that's going to be something that's very nice about the matrix. But that is essentially the types of problems that you will kind of run into with a 2x2 matrix. You have to be able to, A, find the inverse, and then from there, apply it to be able to solve a system, which is what we're going to do next. So setting up the next example. Solve the system using inverses. So you have to pay attention because some questions will be like, solve it doing Cramer's rule or solve it using row reduction or elimination method. So if you don't use the correct method, they could always take away points from you. So even though there are many techniques to be able to use here, I would always say row reduction is king because row reduction has no conditions. You always get an answer. Whereas all of the other techniques, they require like, there's always some kind of caveat, right? There's always something that breaks it. So step 1. Formula. We're going to have to find the inverse, okay? But remember, we're also going to have to convert it into matrix form. So we have AX equals B, and the inverse of A is going to be equal to 1 over AD minus BC. Swap the diagonals, and then make the other two negative. When I say negative, I mean swap them, okay? Step 2, okay, is find A and B. So A is just your coefficients for X and Y. 3, 2, 6, negative 1. Step 3, find, whoops, I forgot B. Can't forget B. 3 and 7. Find your inverse. So the inverse is equal to 1 over 3 times negative 1 minus 2 times 6. And then we got negative 1 and 3, and then negative 2 and negative 6. So those all swapped. And then if we simplify it, we get 1 over negative 3 minus 12, which is a negative 15. So as you can see, this is not going to be super nice numbers. So we end up getting, oops, sorry. It's not going to change the answer, but technically speaking, that should have been negative 2. Actually, no, I take it back. I was right the first time. I was just looking at the wrong matrix. Nope, ignore what I was about to say. Use the original matrix, not the swapped one. Now, personally, leave it on the outside. So actually, let's not even multiply it in. Don't do it, because if you do, you're going to make yourself do more work. Okay. Step 4 is solve for x in ax equals b. Now, I'm going to tell you right now, it's the same thing every single time. So x is equal to a inverse times b, right? We do the multiply both sides by the inverse. I'll do it up here. And so they cancel each other out, and you're left with that, right? So we know what A inverse is. We know what B is. So the inverse of A is going to be 1 over negative 15 times -1, -6, -2, 3. So that's why I say don't distribute, because you're going to have to do matrix multiplication. And you could always do it at the very end. And then 3 and 7, which is equal to 1 over negative 15. And then we get -3 plus -42, so -45. And then -6 plus 21 is a 15. And so we get 45 negative divided by -15, we get 3. And then we get -1. And so that's our x value. That's our y value. So x equals 3, y equals -1. And that's our answer. And that's how you do the matrix inverse method. And I want you to think about this, like if you compare every other technique, right? Row reduction, and then eventually Cramer's rule, when you learn that, you'll kind of realize that matrix row reduction, especially on a calculator, is way better, right? Now, if you wanted to do this on your calculator, you could. So let's do second matrix. Now, if you're going to use your calculator, don't calculate the inverse and then plug that into your calculator. If you're going to use your calculator, just start from the very beginning and don't do any work beyond that. So we're going to do edit. We're going to put our original 2 by 2. So 3, 6, 2, -1. That's A. Second quit, second matrix, go to edit. Let's make a B matrix now. 3, sorry, that should be 2 rows, 1 column. 3, 7. And that's it. Don't make an inverse one, because you're going to take the inverse on the calculator. So second matrix, A, inverse, second matrix, B, and 3, -1. And you get the answer, right? Now, if you wanted to do row reduction, which is what I would recommend, I would go to edit, 2 by 2, make this 3 columns, and then add the B column at the very end, because that's the augmented matrix, right? From the previous section. Second quit, second matrix, hit math, go to RREF, second matrix, A, and you get 3, -1. So you can see that all of these techniques are giving me the same thing. I just personally believe that the row reduction is the best, because if you had infinite solutions, this technique doesn't work anymore. There's no inverse. So, but always pay attention to the directions. Always use the technique that they ask you for, because if you don't, then you will inevitably lose points. One thing mentioned earlier in terms of the 2 by 2 matrix is that 1 over AD minus BC, that's actually something special, and that what leads us into the determinant of a matrix. So the determinant of a matrix is simple yet complicated, because if you really want to know what it means, it's kind of like you got to think about it in terms of what we call transformations of, objects and stuff like that. But for us, we can think of it as a number that just tells us a yes or a no, right? So the determinant of a matrix is a number that tells you a matrix is invertible or not. Well, how does it do that? Well, if the determinant of A is 0, the matrix is not invertible. if the determinant of A is not 0, the matrix is invertible. Okay, and that's it. That's all it tells you. And so the notation we'll use is like det of A, or some people like to use kind of like an absolute value, two vertical lines around it. Those are interchangeable. Some use capital D, some use lower d. And so for a 2x2, the determinant of, so you would do it like this, A, B, C, D is equal to AD minus BC. So that thing that we had on the bottom, that really meant determinant, okay? And then if you want to do a matrix determinant without having to write DET, you could also write it as vertical lines. So if you ever see vertical lines around a matrix, that is telling you that you are taking the determinant of A, okay? So that's another way of doing it as well. And so if you're asked to find the determinant, which you will have to in some of the problems, but you're also always finding the determinant when you are taking the inverse, that'll tell you whether or not it's invertible. So an example of that is straight up, find the determinant of 1, 2, 3, 4. Well, 1 times 4, AD, minus 3 times 2, and that is equal to 4 minus 6, which is -2. So what does that number tell me? It's invertible. And that's all it tells me for now. It can tell you other things in other areas of mathematics. It can tell you some areas of certain shapes, tell you a volume of a weird shape. But for us in this class, it's just kind of like a yes or a no question. Either the matrix is invertible or it's not. Now, if you're wondering, how would I do this on my calculator? Well, you just take your matrix, and you can only take the determinant of square matrices. So if we go back here, let's make this a 2x2. 1, 2, 3, 4. You do second quit, second matrix, and it's option number 2. Sorry, number 1. Number 2 is a transpose. Determinant, second matrix. Oops, that's logic. A, and we get -2. And it's invertible. That's all we get out of it, right? So determinants only work for square matrices. What this also tells us is that A inverse is equal to 1 over the determinant of A times D -B -CA. So I can simplify that formula a little bit more so that it's easier to do. Now, if you're wondering, how would I take the determinant of a 3x3 matrix? Well, in that case, you would kind of want to use a calculator. There is a technique for doing matrix determinants for 3x3s using what we call cofactor expansion, or we could do row reduction, but typically speaking, in this class, we don't usually do 3x3 determinants by hand, but I will show you how to do it on the calculator. And you should ask your instructor if you need to know how to do a 3x3 determinant by hand, because if you do, the optimal technique probably for a 3x3 is something called Saru's method. But for now, we'll just kind of stick with the 2x2. And then if we have to add a 3x3 example, we'll add it later. So we'll do second quit, second matrix, math, determinant, second matrix, A, and then we get -2 just by coincidence, honestly. So that's how you take a 3x3 determinant. So that effectively wraps up the section for inverses and determinants, just being able to take 2x2s. Like really, it's all about 2x2s. So that's what you should focus on, is understanding how to find the inverse of a 2x2, how to apply it to solve a system, and then how to take the determinant of a 2x2 so that you can say whether or not something is invertible.